In this video, we present our paper titled OrcVIO, Object Residual Constraint Visual-Inertial Odometry. This is a joint work from the Existential Robotics Lab at UCSD, and the corresponding author is Shan. It will be presented at IROS 2020. Recent advances in SLAM and visual-inertial odometry have occurred mostly in isolation from the advances in semantic scene understanding. On one hand, state-of-the-art VIO or SLAM approaches can produce accurate trajectory estimation and a geometric reconstruction of the scene. On the other hand, impressive results have been achieved in object recognition and semantic understanding using deep neural networks. Therefore, we propose a joint visual-inertial odometry and object-level mapping algorithm that could generate geometrically consistent and semantically meaningful maps. The key novelty of our work is the definition of semantic keypoint and bounding box residuals, the derivation of the associated closed-form Jacobians, and a tight coupling between online object mapping and camera pose estimation. Previously, category-specific approaches have been used to optimize the pose and shape of object instances using semantic keypoints or 3D shape models. For example, object pose and shape are optimized in the IROS paper using semantic keypoints to provide additional error terms related to object pose in the SLAM vector graph. Moreover, visual-inertial information for object mapping is used in the ECCV paper, relying on a database to retrieve object shapes. Those methods are computationally demanding in general, due to iterative optimization and the reliance on instance-specific CAD models. Category-agnostic approaches use geometric shapes such as spheres, cuboids, or ellipsoids to represent objects. CubeSLAM generates and refines 3D cuboid proposals using multi-wheel bundle adjustment without relying on prior models. Quadric SLAM uses an ellipsoid representation suitable for defining a bounding box detection model. Structural constraints based on supporting and tangent planes, commonly observed under a Manhattan assumption, have also been introduced. Using generic symmetric shapes, however, makes the orientation of object instances potentially irrecoverable. For instance, the front and back of an object become indistinguishable. We use an ellipsoid at the coarse level to restrict an object pose variation. This representation is to some extent inspired by a famous painter who claims that it is natural to represent objects using geometric shapes. We also use semantic keypoints at the Feng level to obtain a precise shape deformation. An object instance is defined by the deformations as well as the instance pose. The IMU-camera sensor provides three sources of information: inertial, geometric, and semantic. Geometric features are the corner features, and semantic information includes the bounding box and the semantic keypoints. Our objective function is to determine the sensor trajectory, geometric landmarks, and object states that minimize the weighted sum of residuals associated with those measurements. We decouple the optimization over landmark and object states from the optimization over the robot state. When a geometric keypoint or object track is lost, we perform multi-wheel iterative optimization over its state based on the latest IMU-camera state estimate. The IMU-camera state is propagated using the inertial observations and updated using the optimized landmark and object states, as well as the geometric and semantic observations. We define the geometric keypoint residue as the difference between the image projection of a geometric landmark using the estimated camera pose and its associated keypoint observation. We define the semantic keypoint residue as the difference between the image projection of a semantic landmark using both the estimated camera pose as well as the object pose and its associated keypoint observation. We use the star map network for keypoint detection and augment the star map keypoint detector with dropout layers to obtain the semantic keypoint covariances. Common filter is used to track the semantic keypoints on an object level. We initialize the semantic keypoint landmarks by stacking the reprojection equations for the same object observed across all frames to obtain a linear system which could be solved via least squares solution. We can reproject the initialized keypoint positions in the image, and we can see that it's very close to the keypoint track observations. To define a bounding box residual, we project the ellipsoid to the image and calculate the reprojection error with respect to the tangent lines obtained from the bounding box. We compute closed-form Jacobians for the geometric, semantic, and bounding box residuals with respect to the object states, which are used in the object state optimization. We propose a framework similar to MSCKF for fusing the observations, but instead of quaternion, we use rotation matrix to parameterize the robot state and derive a closed-form integration for state propagation. The object state is reprojected on the image, where car shape represented by semantic keypoint is the red wireframe, and the green ellipse is the reprojection of the ellipsoid. We compare the precision and recall of OrcVIO on the Kitty raw sequences for object mapping. The results demonstrate that OrcVIO is able to retrieve a reasonable amount of the ground truth objects and provide a high-quality object map. When both rotation and translation errors are considered as in the first 6 rows, OrcVIO is better than sub-CNN, since sub-CNN does not rely on temporal association of objects. Moreover, OrcVIO outperforms sub-CNN and VNN's FNL when only translation error is taken into account, which suggests that the object position estimates are accurate. Thanks for watching this video. For more details, please refer to our project website.